Hello guys, welcome on Tesla Adventures. In this video, I am starting a very complex topic of rigid body dynamics, which is also called as angular momentum. And most of the students, in fact, even some teachers are having doubt in this topic. So let us hope that we'll find out the correct approach to deal with the questions of angular momentum in this video, at the end of this video. So first of all, let me define the angular momentum. That angular momentum is the instantaneous movement of momentum of an object at some point. Now we have already studied the movement of mass in center of mass, and we have studied the movement of force in rigid body motion itself previously, and we know that the movement of force is also called as torque, and the formula for torque is R cross F. So the movement of linear momentum is also called as angular momentum, and in fact some people define angular momentum by the definition that angular momentum is the momentum of a rotating body. So this is absolutely absurd, and this is not correct, because angular momentum can also be calculated for a body which is in the translating motion state. So angular momentum is not necessarily defined for rotating objects only, it can be defined for translating objects also. So angular momentum is the instantaneous movement of linear momentum of an object about some point. So you can see that there is a particle, this is the particle which is moving in the x direction with the linear momentum p, and we have to find out the movement of its momentum about origin. So let us join this particle from origin, and this vector which is pointing from origin to this particle is called as position vector of the particle. Now this position vector makes an angle theta with the momentum, and if we have to find out the movement of this momentum about origin, then that movement of the momentum about origin would be R cross F. Likewise, you may remember the formula for the torque, that was R cross P, in fact R cross F, and the angular momentum is R cross P, where P is the linear momentum, which is mv. So you can also write it as LO is equal to R cross mv, and as m is the constant quantity, it can be taken out, so it is R cross v. So this is the angular momentum. So angular momentum is basically the movement of linear momentum of some body about some point. So this is the first definition of the angular momentum. Now we all know that momentum is a absolute quantity, which means that momentum is obviously the quantity which is not dependent on any point. And in fact we know that momentum depends on the frame of reference, but angular momentum is dependent on some point. So angular momentum is not an absolute quantity. In fact, angular momentum is always defined about some axis or some point. Now this is the second important thing. Now the third most important thing about angular momentum is the fact that most people say that angular momentum is defined only for the objects which are rotating. So this is not correct. In fact, angular momentum of translating objects can also be calculated about some point. So this is due to the fact that in any translational motion and in any rotational motion, you cannot differentiate at any instant. I mean to say that at any instant, the translating motion and rotating motion are the same. And if I will demonstrate this to you, that this is the point which is in the translating motion, and it is always moving in the x-axis like that. And if this point is rotating about the origin like that, but at this instant its momentum is in this direction. So you cannot differentiate the two scenarios by only watching this instant of the particle, that whether it is in the state of translating motion or whether it is in the state of rotational motion. So angular momentum can also be calculated for the objects which are moving linearly or which are only translating. And obviously angular momentum can be calculated for those objects which are rotating as well. Now you can see that this is a point which is moving with some momentum p, and we have to find out the angular momentum of this point p about this point s. Okay, so let us first of all join s with this point, and this is r s vector. Now we know that angular momentum is defined as L is equal to r cross p, and therefore its magnitude would be r p sine theta into L cap, where r p sine theta is the magnitude of the angular momentum and L cap is the direction. Now you can write this r sine theta together, and you can see that if we write the angular momentum in vector form in this case about s, then it would be r cross p, and its magnitude will be r p sine theta L cap. And if I write r and sine theta together, then you can see that r sine theta would be the perpendicular drawn on the momentum vector from point s. So if you have to write the scalar form of angular momentum and its magnitude only, then you can say that angular momentum is r perpendicular into p, where r perpendicular is the perpendicular drawn from that point s on the momentum vector, like that. Okay, so this is rs and this is rs sine theta. So in this case, in the second case, you can see this one. You can also write, first of all, let us write the angular momentum in vector form. So in the vector form, it is r cross p, and obviously we have already written that r cross p is equal to r p sine theta L cap. Now we are writing p sine theta together. So p sine theta is the component of momentum which is perpendicular to r. So we can also write that angular momentum in scalar form ls is equal to r into p perpendicular. So you can see that if we draw the component of momentum which is perpendicular to this r vector, then this is p perpendicular and it is p sine theta. So in either of the way, you can write down the magnitude of angular momentum, and you can calculate the angular momentum in scalar form. Now the direction of angular momentum. As we have already learned in the vectors that in cross product, if C is equal to A cross B, then the C would have the direction which is perpendicular to the plane containing A and B, and therefore that the direction of C can be determined by Fleming's right hand screw rule. So to determine the direction of angular momentum, let us see this scenario, that if angular momentum is equal to rs cross p, then rs is written before p, then we have to curl our fingers of right hand starting from rs towards p, like that. So if we curl our fingers like that, then thumb, which is opened straight, will be pointing in the upward direction. Therefore this thumb would be representing the direction of angular momentum. So likewise, any other quantity, any other vector quantity which is the result of cross product of any other two quantities, the direction of angular momentum can also be calculated by using Fleming's right hand screw rule, like that. So starting from, I'm telling you again, that is starting from R and curling towards P. So start from R and curl your fingers towards P, then thumb will point in the upward direction and therefore this thumb will represent the direction of angular momentum. In this first type of questions which are based on angular momentum, so in this first type we are calculating the angular momentum in pure translational motion. Now in these kind of questions only there will be two different type of questions. The first question would be in the form in which the momentum vector and the position vector of that particle about some point would be given to us, and therefore we have to find out the angular momentum. So in this first type of question we have to use the vector form of formula for the angular momentum. Now we know that the mass is given as 2 kg and velocity is given as 3 I cap and 3 j cap. So the linear momentum P will be equal to mv, and therefore linear momentum P will be 6 I cap plus 6 j cap. Okay, now the position vector of this particle it can be calculated by the coordinates. So the position vector of this particle with respect to s is 2 I cap plus 3 j cap. Now we can find out the angular momentum by the vector form, and it is r cross p. So r vector is 2 I cap plus 3 j cap cross with 6 I cap plus 6 j cap. So you can see that 2 into 6 is 12 and I cross I is 0. Now 2 into 6 is 12 and I cross j is k, plus 3 into 6 is 18 and I j cross I, this is j cross I, and j cross j is 0. So this is I cross j is k, so 12 k cap, and j cross I is minus k, so this is minus 18 k cap. So this is minus 6 k cap, which means the angular momentum of this object about point S is minus 6, and the direction of this angular momentum is towards minus j cap, going inside the plane. Now let's move on the next question. In this question, a particle is projected with some initial velocity of u at an angle of theta with the horizontal. The mass of the particle is m, and we have to find out the angular momentum of this particle at any time t about the origin. In fact, about y-axis in the first case and about z-axis in the second case. So first of all, let us locate the particle, and let us assume that this particle has a coordinate of x comma y at any time t. So the x component of the particle will be x will be equal to u cos theta into time, and the y component of the particle will be equal to u sin theta into time minus half g t square. I hope you are well aware of these equations, and we have already discussed them in the projectile motion. So this is x and y. Now we know that in the first case we have to find out the angular momentum about y-axis. Now let us also find out the velocities. So the velocity of the particle towards x-axis will be u cos theta. It always remains the same. And towards y-axis is, let's suppose, vy. So vy will be equal to u plus at. So uy was u sin theta, and g is negative. So this is minus g into t. So this is vy. Now we know that if we extend the momentum vector of horizontal momentum vector, this is u cos theta, then this momentum vector would cross the y-axis. Therefore its perpendicular distance from the y-axis would be 0, and therefore the angular momentum due to this horizontal velocity will be 0. about y-axis. So angular momentum about y-axis would be only the distance, perpendicular distance of that particle from y-axis, which is x, into the perpendicular momentum about this vector x. So this is x multiplied by p perpendicular. P perpendicular is m vy, and x is equal to u cos theta into t, and vy is equal to u sin theta minus gt. So this is the angular momentum about y-axis. The direction of this angular momentum can be calculated by right hand screw rule. This is x vector and this is momentum vector. So if we curl our fingers starting from x vector towards momentum vector like that, then our thumb of right hand would point towards the direction which is inside the plane of the board. So the direction which is inside the plane of the board is minus k cap. So this is along with the direction of minus k cap. So I am telling you again that you have to curl your fingers starting from x vector towards momentum vector, and this direction of thumb would be pointing inside the plane. So the direction of the thumb is towards minus k cap, minus z axis. Now we have to find out the angular momentum about z axis. So this is the z axis which is coming out of the plane like that. So let us first of all join the z axis with this particle like that, and this is r vector. So angular momentum about z axis will be r cross p, where p is the net momentum. So r vector is x I cap plus y j cap. I have already calculated x and y, and p vector will be m into u cos theta I cap minus m into vy j cap. Okay, so this is let us write this as uy, ux in fact. So this is p vector. So we know that L is equal to r cross p, and r cross p can be calculated by determinant or by simple method. So by using that determinant approach, or we can calculate by simple method. So let us calculate by simple method. So this is x I cap plus y j cap cross with ux I cap minus vy j cap, and m is taken common, mass. So this is m, and I cross I is 0 while I cross j is k. So this is m into x vy minus k cap. This minus is due to this one, and j cross I is minus k as well. So this is minus y into ux, and j cross j is 0. So the angular momentum about z axis will be equal to m, and minus k cap is common, and and this is x vy plus y ux. So this is the angular momentum about z axis. Now let's move on the next question. In this question, a particle is projected with some angle theta with the ground with some velocity u like that from point O. Now we have to find out the angular momentum of this particle about this point of projection O when it is at the starting point at this point, and when it is at the highest point, and when it just strikes the ground again. So first of all, let us find out when it is at the starting point. So obviously when the particle is at starting point, and we have to calculate the angular momentum of that particle about the same point at which that particle is situated. So the angular momentum would be 0 because r vector would be 0. So the first case in which we have to find out the angular momentum about point O, then it would be 0 initially at t is equal to 0. Now in the second case, when the particle is at highest point. So when the particle is at highest point, you can see at highest point the particle has only one velocity, which is u cos theta, which is the horizontal velocity, and hence the angular momentum of the particle can be calculated by the formula L at a about O. It means that L at a about O is equal to r perpendicular into momentum. So the momentum at point A is mu cos theta and the perpendicular distance is this one. So this perpendicular distance is the maximum height attained by the projectile. So this is h and mu cos theta. Now the direction of this angular momentum can be calculated by this one. So you have to curl your fingers from h towards momentum. So you have to curl your fingers of right hand in clockwise sense like that. So your thumb would be pointing in the negative z-axis direction. So this is minus k cap. And the maximum height is obviously equal to u square sine square theta by 2g, and this is mu cos theta minus k cap. So this is the angular momentum when the particle is situated at point A. Now when the particle is situated at point B, then it would be having the velocities in x-axis, which is u cos theta, and in y-axis, which is u sin theta. Because we know that at the moment when this particle will again be on the same level as that of the point of projection, which means that when it would be again striking the ground, then the velocity of this particle would be same as that was initially at point O. So initially the y component was u sin theta and the x component was u cos theta. So finally at point B the y component will be u sin theta and x component will be u cos theta. Now if we extend this x component behind, then it is passing through point O. Therefore the angular momentum due to this x component about O will be 0, because it is itself passing through point O and the perpendicular distance of this component from the origin is 0. But if we have to find out the angular momentum about O of the y component, then the angular momentum of particle at B about O will be mu sin theta, which is this component, into perpendicular distance from O. So the perpendicular distance from O is given as range, and range is known to us, which is u square sine 2 theta by g. And the direction of this angular momentum would also be in minus k cap, because radius vector r vector is like that and momentum is like that. So we have to curl the fingers of our right hand starting from R towards P. So curling the fingers from R towards P would be curling them in clockwise sense, and if we curl them in clockwise sense, then our thumb would be pointing in the downward direction, which is minus k cap. So this is minus k cap. Now let's move on the next question. In this question, it is given that there is a particle which is moving with constant velocity towards x-axis, and it is initially located at a point which is having the coordinates 0, d, this point. So we have to find out the angular momentum of this particle about the origin at this instant of time as well as at some later instant of time. So the angular momentum of this particle about the origin at t is equal to 0 will be mu into r perpendicular. Now the perpendicular distance of the momentum vector from the origin is d itself, you can see. Then the angular momentum will be mu into d, and the direction of angular momentum can be calculated by r cross f. If this is r and this is p, in fact r cross p, I beg your pardon, then you can curl the fingers of your right hand from R towards P like that. So it would be curling in clockwise sense like that. So the thumb would be pointing in the downward direction. So the direction of angular momentum would be minus k cap. Okay. Now at some later moment of time, when the particle is situated at this point, at t is equal to t, the momentum is still mu, and if we extend the momentum vector and we draw the perpendicular, then the momentum the perpendicular distance would still be d. So the angular momentum at t is equal to t will be again mu into r perpendicular, and this will be mu into d, and the direction would be minus k cap, because again if we curl the fingers of right hand from r towards p, then thumb will be pointing in the downward direction. So this was the complete analysis of angular momentum calculation in pure translational motion. Thank you.